さあ、ちゃんと撮影しよう。今日は川の撮影です。
And these results ended in the early 80s. So what they prove is that having dimension is between 3 and 6. So this closed Riemann manifold. So always admits at least one closed, smooth, closed, embedded minimal surfaces. The dimension range is due to the compactness theory and has been extended by Shen-Simon to pair dimensions, allowing a single site. So motivated by this theorem, so Yao poses a favors conjecture in the 80s. I think that's another special year for geometry at the institute where Yao poses conjecture. You see that every closed 3 manifold so admits so infinitely many closed minimal surfaces. And we know that this has been solved by combining the work of Fernando Marquez, Andre Neves, and Antoine Song. It happened recently last year. Okay, so what I was doing is related to a program proposed by Fernando and Andre, so towards solving this conjecture. So the moral of the theme of this conjecture is we try to establish a Moore theory for the area functional in a space of hypersurfaces. Area functional. Okay, so then the first question would be, in which space are we going to try to find a Moore theory? So the space they use is denoted by that. So this is the space of Moore2 hypercycles. So it should be the one of the connect component. So of the space of Moore2 cycles in M. I mean the connect component containing 0, containing all amplitude sets, whatever. So for example, a way to visualize this is as follows, for which I'm going to give a proof later. So suppose that this is ambient space. So an element would be a hypersurface that separates the manifold into 2 parts. So say this part is omega, this is m minus omega. So we should say that this is in the N. So if and only if this is written as the boundary of some domain, and that's the same as the boundary of the other side, since we use the D2 coefficient, so we don't distinguish orientation. I mean, this is an intuitive way to understand, and I'm going to give you a heuristic proof later about this fact. Okay, so the reason to study the space of Moore2 hypercycles is because this space has a very fruitful topology. So early work of Angren. So we calculate all the homotopy group of this huge space. So using Z2, so the fundamental group is Z2, and any higher homotopy group is 0. Okay. So then from the basic homotopy theory, we know that this huge space is weakly homotopic to the infinite dimensional projective space, so weakly homotopic. Particularly, we know that the cohomological ring is very nice. So using the Z2 coefficients, so this is a polynomial ring over Z2. And so here this lambda is the generator. So I'm going to give you a geometric interpretation for this generator very soon. Okay, so this is a fruitful structure. It's very natural to think about the area functional being defined over this space. And so a very rough question is, can we use a topology here to give a critical point of the area functional, which would be minimal surfaces. So if you're successful, then we have so many topology, then you should produce at least a list of infinite many minimal hypersurfaces. So that's their basic idea based on the part of the topology. Okay, so to continue, we move a little bit to analysis. So that's a notion of a volume spectrum. So we try to formulate the relation between this space and the critical values of the area functional. So the notion was first mentioned by Gromov in 1988, and then amended by Larry Goose in 2009, and used successfully by Fernando and Andre. So this is 2013. So to describe the volume spectrum, let's quickly remind you how can we define the spectrum for the Laplace operator, or even for a simple finite dimensional self-adjoint symmetric matrix. So if you have a matrix, then you can formulate calculate the associated radial quotients. So say give a p-dimensional plane or k-dimensional plane in Rn, you can maximize the radial quotient and then take the infimum over all p-dimensional planes. Using this way, you can produce all the eigenvalues for symmetric matrix, and you want to generalize that to this nonlinear problem. So the first thing is, how do we define a k-dimensional p-dimensional plane in this nonlinear space? So that's a notion of p-Swaypot introduced by Fernando and Andre. So let me define the p-Swaypot. So we have a continuous map from some space into Dn. So this X would be a parameter space, finite dimensional parameter space. So continuous map is called a k-Swaypot. So where k is an integer. So if it satisfies the following cohomological condition, so we pull back the generator up to the case cup product, then this is elements in the case cohomological group X. We require this is not 0. Okay. So that's a cohomological condition for k-Swaypot. So from the definition, we first know that so the dimension of the top strata of X should be greater or equal than k. So if less than k, the case cohomology should be 0. And to give you some feeling about what we can take for the parameter space, so definitely you can take X to be say R P k prime for any k prime greater than k, and or you can take X to be R P k prime, connect them with some other space as far as you make it satisfying this condition. So it is a legitimated generalized k-dimensional plane. Okay. So finally, let me quickly explain what that means for a one-Swaypot. So for one Swaypot, we will take X to be a circle. So then you have a one-parameter family of hypersurfaces. For that to be a Swaypot, we require that the union of them Swaypot the whole manifold. So intuitively, for one parameter family to be a one Swaypot, we require to cover the whole manifold exactly once after cancellation of orientations. Okay. So that's the reason why we called it a Swaypot, because the one-dimensional case, and then we generalize call it a k-dimensional Swaypot when k is greater than 1. Okay, so this is the notion for that's the notion for generalized k-dimensional plane. So then we can define the case volume spectrum just by mimicking what we do for eigenvalue for symmetric matrix. So it denoted by omega k. It's a real number, non-active real number, depends only on the metric and mean space. So what you do is you first take an arbitrary k-Swaypot, and then you take the maximum area, and then you take infimum over all possible k-Swaypots. So if you think about how you do this for symmetric matrix, the only thing you change is you change k-Swaypot to a k-dimensional plane and change the area function of the radial quotients. So it's really very analogous things here. That's also a reason why I would say this is an analog for Uhlenbeck theorem, because it deals with radial quotient while we deal with the area function. So we know that this satisfies the following inequalities. So it's a non-decreasing sequence of positive numbers. So I would say that this inequality, this strictly fine, is very hard to prove, and it's due to Almgren in his very first paper. Okay, so now we define the critical values. So you would ask whether these critical values are associated with critical points, which are minimal surfaces. So that's a hard analytical part of the theory. So that's a Mimax theorem. So I should mention a few names. So Almgren proved the existence of the solution, and please prove the regularity for the dimensions between 3 and 6, and then Shin-Simon. So this is 81. Generalize to all dimensions. Well, in high dimensions, you should allow single set of codimension 7. And Fernando and Andre generalizes to the D2 coefficients together with very powerful Morse index upper bounds. So they generalize to the D2 coefficients in 2013, and then with the Morse index estimates in 15. So combining all the words, we can state the theorem as follows. So let me only state the case when we have regular minimal surfaces. So I restrict to lower dimensions. So for any integer k, so there exists a disjoint collection of smooth, closed, connected, embedded, so minimal hypersurfaces. So which I should denote by sigma ki. So I is from 1 to lk, such that so the case volume spectrum can be written as the sum of the areas. However, you need to have integer coefficients here. So these are called the multiplicities. And moreover, Fernando and Andre proved that the sum of the index of the support is bounded from above by k. Okay. It's a bit tight here. So this equation says that the volume spectrum are realized by the area of smooth closed embedded normal hypersurfaces, but with certain integer multiplicities. And the second is the contribution from Randall Andre. They prove that the Morse index, for which I will give a definition very soon, is very analogous to what Matt defined for the Einstein and the Yang-Mills functionals, expanded from above by k. So that's because we're running a k-parameter variational theory. Okay, so I only stated this. I mean, they only prove the regular case. Okay, so one of the remarks is, why do we have these integers? So this set of integers or multiplicities arise due to the use of compactness theory for minimal surfaces. So we all know that if you take a limit of sequence of minimal hypersurfaces, even a connected guy can collapse into a multiple cover of the limit. For instance, the limit blow down of the catenoid would be a double plane. So these uses the Shin-Salmon-Yau curvature estimates and compactness. So this is the compactness in higher dimensions. So the limit a priori will always have multiplicities. Okay, so let's try to see what we would have using this theory together with this topological structure. So if you apply the theory to each of them, so if you apply the theory to the first volume spectrum, you produce a non-trivial closed minimal surface, which would be the Angron-Pitts theorem. So if you apply to the higher volume spectrum, you may get just integer cover or multiple cover of the previous minimal surfaces. So that's a big obstacle to the solve of the Yost conjecture, wherever the solution uses indirect arguments. So motivated by Uhlenbeck's theorem, you would say, can we ask a similar question? I would imagine that's one of the motivations for Randall Andre made this conjecture. So you just ask whether you can have them all identical to 1 in a generic set of metrics. So they first made the conjecture in 15, then they strengthened that in 18. So the conjecture would be still for the smooth dimensions. So for bumpy metric, I'm going to explain to you what does that mean, but we know that the set of bumpy metrics are generic, so corresponding to a generic set of metrics. So the set of minimal surfaces for each k are all two-sided and have multiplicity 1. That's so-called multiplicity 1 conjecture. Yeah, as I said, that analog of property A, that for the Laplacian for the linear problem, all eigenspaces are one-dimensional. So here, just say that these coefficients are all 1. I'll present a proof for this conjecture, but let me first explain you the terminologies I use. Say what does it mean for two-sided hypersurface, what does it mean for a metric to be bumpy, and also how do we define precisely the Morse index for the area functional. So sigma is two-sided. So there is this unit normal. So vector fields. So if you can find everywhere unit normal vector field, this is two-sided. You can say a plus and minus side. Okay, so once we have a two-sided minimal hypersurface, let's talk about the second variation. So this time I'm considering a vector field that's a scalar multiple of this unit normal. So if you push a hypersurface along x and take the second derivative of the area functional, you would have the following formula. So this is the integral of Laplacian phi square minus, so this is the Ricci curvature of the ambient space, evaluated as a normal, plus A is the second fundamental form square, this second fundamental form square. So this is a zero order term. It's also a Schrodinger type operator. And if you want to write it, that's minus phi L sigma phi. So there's L sigma is the Jacobi operator, that's minus Laplacian, minus, so this is a Ricci term, nu plus A square times phi. So that's the second version formula. So then the Morse index, this is denoted by index sigma. It's just the number of negative eigenvalues of this Jacobi operator. So that's very much the same as what I talk about the Yang-Mills functional and this Einstein functional for Einstein metrics. Okay, so now we can define what does it mean for bumpy metric. To be a bumpy metric, we require all closed minimal immersions to be non-degenerate for the second variation. Is bumpy with every smooth closed minimal immersion. Sigma is non-degenerate. Or if you have a solution, it has to be constantly zero. So that's the definition of a bumpy metric. As a theorem of Wainwright, So we prove that the set of bumping metrics are generic. This is a generic set in the Bayer sense. Okay. So then this conjecture can be viewed exactly as analog of Uhlenbeck theorem A. So generically, the eigenstates are simple. Okay, so I'll just present a proof of the thing. So this conjecture is true. Okay. So let me quickly remind you what we were trying to do along the direction of proving this conjecture. So people first tried to look at the problem for this one parameter Mimax. So the pioneer work was done when the ending metric has a positive G curvature, and that was I think one of the breakthrough work in the field of Mimax theory by Fernando Andre in 2011. And then I generalized this in my thesis and in future paper to higher dimensions. And later, so Katover, Marcus Nevis, suggested all the results and give the satisfying multiplicity one result for positive Ricci for one parameter Mimax. And for bumping metrics, or the one parameter, so Fernando and Andre also give a very satisfying answer, which is that all the one parameter Mimax has multiplicity 1 for bumping metric. So this is shortly after this paper. And last year we realized another big breakthrough. That's for 3 manifolds, but for all k. So that was the work by Otis, Chodosh, and Christos Mantolidis. So they proved there's a conjecture for the Alencon setting. So there's a mirror conjecture in the setup of Alencon equations, and they completely solve that conjecture. So that's the history we know about this whole story. Okay, so any questions or comments up to here? So let me just briefly discuss a little bit about applications, and I'll give you a bit of proof of one application to give you a little bit of flavor of what I'm going to use. So definitely the first application would be a direct proof of partial answer to Young's conjecture for bumping metrics and for positive Ricci curvature metrics. So I won't state the result here because I think you all know what that means. So another interesting application I'm excited about is the weighted Morse index upper bound conjecture by Fernando and Andre. So let's go back to see the original statement about this Mimax theorem. So Fernando and Andre proved that the sum of the index for the support is bounded by k, but you would imagine that you want to count in the multiplicity in this index upper bounds. So if you're able to perturb the metric to make sure multiplicity is always 1, then you can obtain it by taking a limits. So now I'm going to state the version for that. So still we are in these lower dimensions. This time G is arbitrary metric. So then, for the set of minimal surfaces obtained in the Mimax theorem, we have the stronger Morse index upper bounds. So the sum, I need to separate the collection of minimal surfaces into 2 groups. This 2-sided group and 1-sided groups. So if sigma I is 2-sided, so we're allowed to multiply the index by the integer multiplicity. And if it is a 1-sided, so actually, I proved in my thesis that if it's 1-sided, the multiplicity always has to be an even number. So you can divide it by 2, multiply. So this is bounded by k. So the remark is that so mi is an even integer if sigma I is 2-sided. Sorry, 1-sided. Okay. So this is a stronger version for the Morse index upper bounds. Okay, concerning the Morse index upper bounds, Fernando and Andre were able to prove that for bumping metric, what you get, the sum is exactly k. It's not only bounded from above the k, it's also bounded from below the k, the sum. Okay, so the proof it would be a direct corollary of multiplicity 1 and the Morse index upper bounds, but I'd like to present some of the details so as to prepare you for some of the technical work later. So let's do it here. So I proved that theorem using the assumption of multiplicity 1. Okay, so for arbitrary metric, we perturb it to be bumpy. So take a sequence of bumpy metrics, which denoted by G upper, such that G upper converges to G. Okay. It's a simple fact that from the definition of the volume spectrum, this corresponding volume spectrum for G upper will converge to that of G. So then we apply the multiplicity 1 together with upper bounds to this guy, and so as to see what happens in the limit. So we know that so omega k G upper is the sum of the area of sigma upper I. For simplicity, so later I will try to assume there's only one connect component, so the proof will be the same. And so the sum of the Morse index bounded from above by k. So then it's placed to apply the compactness theorem for minimal surfaces. subsurfaces, which was proved by Ben Sharp based on the work of Shin-Simon Yao and Shin-Simon. That's a very nice theorem. Okay, so the idea behind Sharp's compactness theorem is that if you have a sequence of minimal surfaces with uniformly bounded area and uniformly bounded Morse index, you can localize so that away from at most k points, you always have a stable piece. And for stable piece, so Shin-Simon Yao and Shin-Simon proved that they have uniform curvature estimates. They can take subsequence to get a smooth limit, and then you do removable singularity. By his theorem, so subsequence of so we'll converge this to a smooth limit.